And you can see the screen, okay?
Yes, it's perfect. Thank you.
Great, thanks. All right. So last time we were talking about the structure of renormalization group flows, and we introduced the concept of the critical manifold. So the critical manifold is a manifold is just a subspace of some space, just a fancy word for that. And what we found was that this critical manifold, every point on this manifold, the points on it representing different physical systems would flow into the critical fixed point on that manifold. And therefore, all those points represented systems with Hamiltonians that were seated at the critical temperature Tc. So that's that's what we introduced, and we realized that this is part of the reason for universality, because you might say, well, one of those systems was the nearest neighbor Ising model, one of those systems was the 134th nearest neighbor Ising model. Both of them flow, suppose they all both flow into the same critical fixed point, then that would say that those two different models, ostensibly completely different, actually behave the same in terms of their critical behavior. But I pointed out that that's not the only reason for universality. And the reason is that when we talk about critical behavior, we mean critical behavior of the critical manifold. For example, looking at T minus Tc and looking at how the heat capacity of specific heat diverges as T tends to Tc with some exponent alpha. We want to understand these exponents alpha, so we have to be of the critical manifold. So then what we did was we said, well, let's have a look at the at points off the critical manifold. And so what we did was we said, let's write the coupling constants as the critical coupling constant plus some deviation from criticality. And that's sketched in the picture at the bottom of the screen. So here is my cartoon of coupling constant space. In yellow is a critical fixed point. And then we start off with some physical system, some deviation away from that critical fixed point. And then after a renormalization group transformation, the deviation moves to a different point, delta Kn prime, in that space. And so what we are going to do now is expand the Hamiltonian about the critical fixed point. So the Hamiltonian depends on the coupling constants. So now we're going to set the coupling constant equal to K star, the critical fixed point, plus some deviation. That means that the Hamiltonian will itself have a deviation. And what we're going to ask now is, how do the coupling constants change as we do renormalization group transformation? So that's shown here at the top of the right-hand panel. So here we're saying after a renormalization group transformation, your coupling constants K have now gone to the coupling constant vector K prime. In component form, Kn prime is now some function of the previous values, the vectors K. And what we're going to do is expand that about the critical fixed point of the renormalization group transformation. And so then we're going to have a transformed deviation away from the critical fixed point. Okay, so what we're going to do now is we're going to linearize this function. So we're going to write that Kn prime is, I can think of this as being a function of K1 star plus delta K1, K2 star plus delta K2, K3 star plus delta K3, etc., etc., etc. So I can just now do a Taylor expansion of that. So that is equal to Kn star plus, and then now doing a Taylor expansion. So it's going to look like this, delta Kn prime by dKm evaluated at, this is an m, evaluated at Km is equal to the critical value times the change in the coupling constant Km, and then I'm going to sum over the index n. So this is the linear, this is just the Taylor expansion of this function. And then the next terms are going to be of order delta k squared, and we're going to be neglecting those. So I can summarize this equation by writing it down in matrix form. So I can say then that delta kn prime, the change in the nth component of the coupling constant as I make a renormalization group transformation, is then some matrix m of nm times delta km, and then I'm going to sum over the index m. So this derivative here, this derivative over here, this is evaluated at the fixed point. So the k's have their values at the fixed point. And so this is just a number. And it's just the derivative of the renormalization group transformation at that fixed point. So I'm going to call that number the matrix MNM. So this is then defined to be dkn prime by dkm evaluated at all the coupling constants are evaluated at the critical fixed point value. And that matrix then, I'm going to refer to this as the linearized renormalization group transformation. So I've got a very complicated nonlinear function, which is the renormalization group transformation. And now I'm going to linearize it. And so there's nothing to stop me linearizing it as long as I stay close to the critical fixed point. And so now we need to look at the properties of this linearized transformation. So now we're going to look at the linear algebra of this matrix M. So the first thing is you might say, well, we're now doing linear algebra. And we've done linear algebra up the wazoo in physics. We've done quantum mechanics. We know all about Hilbert spaces and stuff like that. We're really, really good at linear algebra. Okay? You might think that, but you'd be wrong, because in physics, the operators are Hermitian, and so the matrices have a structure. They're symmetric or they're Hermitian and so on and so forth. There's nothing here to make M symmetric in general. So first of all, M is not usually a symmetric matrix. So what that means is that when you look at the eigenfunctions and eigenvalues, the eigenvectors and eigenvalues of a matrix, actually there's two of them. There's a set that is on the right-hand side and a set that's on the left-hand side on the dual space. And they are not the same as they are in quantum mechanics because the system is not Hermitian. So we'll talk about that. So we're going to have the concept of a left and right eigenvector, and left and right, well, the eigenvalues actually turn out to be the same. So that's the first thing. So there's going to be a slight twist for that. In order to explain this to you easily, I'm going to pretend that the matrix is symmetric for now. But when we actually do this calculation in real life, it will not be symmetric. Okay, and I'll show you how to generalize it, but I'm not going to spend a lot of time on doing that because we won't need to do it. Okay, so if it's not a symmetric matrix, what that means is that its eigenvectors are not what? What will that mean for the eigenvectors?
Hermitian.
Well,
when we take the conjugate, then answer.
so what does that mean for the eigenvectors?
They're not real.
Well,
values are not real.
the eigenvectors will not be orthogonal. So we're talking about the vectors themselves. So the vectors will still be in the space, but the eigenvectors are not orthogonal. Okay, so it's going to be different. So there's going to be two classes. There's going to be left eigenvectors, and I'll explain what I mean by that. Well, you know it already. Left eigenvectors are not equal to right eigenvectors. Go back to quantum mechanics. Okay, you have a bra and you have a cat. right? In quantum mechanics, they're basically easily related because you have a Hermitian operator. Here, they're not. Then it's not like that, and so that's going to be different. Okay. What that means is then if it's not orthogonal, that means that M is not in general diagonalizable. Okay, there's no theorem that says you can diagonalize any matrix. It's not true. Okay, the best you can do is put it into Jordan normal form, if you know what that is. So it's going to be more complicated. And then the other thing is that the eigenvalues, I think this is what you were saying, Amrit, the eigenvalues are not necessarily real. And that gets into a really, really interesting problem, which I'm not going to go into. Okay, so what we're going to do next is our first pass through the formalism. What we're going to do is we're going to pretend that M is symmetric. And there are cases where it can be. And then once we've done that, the extension to non-symmetric is straightforward. And we won't really need it for what we're going to do in this class. Then what we're going to do is we're going to, the strategy is going to be to expand the renormalization group transformation near the fixed point in terms of the eigenvectors of M. And then what we're going to see is that there is a physical significance to the eigenvalues. And in fact, what we're going to discover is that, what use is all this? Well, we're going to learn how to classify these eigenvalues. And we're going to see the terms relevant and irrelevant. And we won't say much about this, but in general, there's a third category, marginal. So this is a classification of these eigenvalues, and what they do, we'll see, is very interesting in terms of the critical manifold. We're also going to see that the consequence of this is that we can derive Kadanaugh's assumptions Remember that Kadanoff assumed that that when we scale to scale L, TL goes like T times L to the Y sub T, and so on and so forth. So we made those assumptions in Kadanoff's block spin picture in order to get the result that we knew that we wanted. But now we're going to see what is the justification of that. So we're actually going to be able to derive that. And then what we're going to do is we're going to then construct the renormalization group flows near a critical fixed point. So we're going to see that we have what's called an RG flow diagram. And I sort of drew a simple one, a one-dimensional one, last time, and we're going to look at that and see what the physical significance of it is. And what we're going to find out is that this RG flow diagram then ends up telling us the phases of the system. It tells us the universality class. and we end up with an understanding of universality, a full understanding of universality. Okay, so that's the picture. So now let's go ahead and get started. And what we're going to do first is we're going to look at how, if we're near a critical fixed point, we're going to ask how does the renormalization group transformation transform, and we're going to expand everything in terms of the eigenvalues of the matrix M. So let's do that. So the next step is the linear algebra of the matrix M. So the right eigenvalues, so the right eigenvectors, they're defined like this. You take the matrix M, it acts on the right eigenvector, and then it produces a number, and then the original eigenvector coming back. Of course, there's many of these, so the eigenvectors are labeled by sigma, and so the eigenvalues are labeled by sigma, like that. And then this lambda is the eigenvalue, but it's the right eigenvalue, so I'm going to put a subscript r on that. So that defines what we mean by a right eigenvector, and this variable sigma, this labels the eigenvalues and eigenvectors. Okay, so now let's do the left problem. So the left eigenproblem. So then what you do is you take the vector on the left going into the matrix M, and that produces the matrix on the left times some number. That number will be the left eigenvalue, and we'll label these things by sigma prime. Something like that. So this is like taking a row vector or a column vector and multiplying them by a matrix and getting another row vector or a column vector coming out. So that's what we mean by that. And now what I'm going to show you is there's some simple theorems, some simple results. So the first theorem is that if I take the left eigenvector with label sigma prime, then that is orthogonal to the right eigenvector at sigma, as long as sigma is not the same as sigma prime. And the proof of that is fairly straightforward. Let me label these equations. So if I'm going to label this equation, equation 1, and label this equation, equation 2, then the proof is this. I take I take the left eigenvector labeled by sigma prime and dot it into equation 1, and I do the same thing for equation 2. So I take equation 2 and then right dot it with the right eigenvector of sigma. And both of those two things together are going to give me that E L sigma prime dotted with the matrix M acting on E right of sigma. So I'm going to get that on the left-hand side of both equations. Okay. So now what I'm going to do is now subtract these two equations from each other. And if I subtract them from each other, then what I get is E L sigma prime dotted with E right sigma times, on the right-hand side, I have just the eigenvalues. So on the right-hand side of each of these equations, I have these eigenvalues over here and over here. So what I'm going to get when I do that is I'm going to get over here lambda of sigma minus lambda of sigma prime, and that is equal to 0, and so therefore what I've learnt is that that this has to equal 0, and so therefore this is like so, and so if the eigenvalues are not the same, assuming that they're all different, then that means that the EL of sigma prime is perpendicular to E right sigma. So that's the first thing. And if they are the same, if I set sigma equal to sigma prime, then that tells me that lambda right of sigma is equal to lambda left of sigma, and so the right and left eigenvalue spectrum is exactly the same. Okay, so that's just very, very simple linear algebra. Okay, so that's that. So that's really the only generalization that we need. But now what I want to do is derive the Kadanoff assumption. So you'll remember that Kadanoff had two assumptions. Assumption one was that the block spin Hamiltonian had the same form as the original Hamiltonian, whereas the assumption number two was that after I course grading, the reduced temperature transforms as T L to the Y sub T. So that was his assumption, and now what we're going to do is we're going to derive that. Okay, so let's now go back to the eigen problem. For the renormalization group transformation, which is linearized, so that's M. M, of course, is labeled by what the renormalization group transformation was, so that remember ML is the linearized form of the original renormalization group transformation about the critical fixed point. So therefore, since the renormalization group transformation depends upon L, then the matrix, the linearized matrix M, also depends upon L, and so I'm going to put it as a superscript. So therefore, when I write M acting on the eigenvector, then that gives me lambda L of sigma E, and this is of sigma, and this is of sigma. So what I'm going to do now is we're going to for simplicity, we're going to assume we're going to ignore the non-symmetric nature. So then once you see the result, then you can extend it yourselves to the non-symmetric case, and it's also in my book if you aren't able to do it. Okay, so this is the eigen problem for the linearized matrix. Now remember we defined a thing called the semi-group property. Of the renormalization group transformation. Let me just remind you what that was. What we said was, suppose I've got a system and I coarse grain it by an amount L1, and then I subsequently do a coarse graining by an amount L2, then what that's going to give me is it's as if I had done a renormalization group transformation by an amount L1 times L2 acting on the original starting point in coupling constant space. So this we call the semi-group property, and we called it semi-group because the point about the semi-group is that there is no inverse. But this is a group composition property. And so therefore, what this means is that this must be shared by the linearized renormalization group transformation. So the linearized RG also obeys this. And so we can write down that M of L acting on M of L prime is equal to M of L times L prime, like that. Okay, so that's what the semi-group property of renormalization group means for the linearized renormalization group transformation. So now let's see what happens, what it means for the eigenproblem. So go back to this equation over here, and now substitute this into the eigenproblem. So again, I'm going to let you satisfy yourself that this is correct, but what you're going to get is that the eigenvalues satisfy this property as well. So the eigenvalue lambda L prime of sigma is equal to lambda sigma of L prime, like that. So this is what the renormalization group semi-group property means for the eigenvalues of the renormalization group transformation. Now, the thing I want you to remember here is that when I write down the eigenvalue, look like this, what that means is that the eigenvalue is some function of L. Okay, it depends on L. The renormalization group transformation depends on L. So the linear renormalization group transformation depends on L, and therefore the eigenvalues depend on L. Okay, what we're going to do next is we're going to ask, what is that function? Can we determine what this function is? So what's coming next is the question, can we figure out what this functional form, what this function actually is? And the answer is, well, we're going to figure it out. Whatever function it is, I'll come to you in a minute, not every function will satisfy this equation. So only a certain function will satisfy this equation. So can we figure out what this function is? The answer is yes. And only one specific functional form of lambda of L will obey this equation. Okay, so let me show you how we do that. Andrew, you had a quick question?
I just, maybe I missed, but I wasn't quite certain why you have the different superscripts on M. I thought M was one matrix. Now you're saying that one.
Well, remember, whatever that matrix is, it's a linearized form of the renormalization group transformation.
Okay.
The renormalization group transformation depends on what the block spin size is. So it depends on L. Since R depends on L, then the linearized function must also depend on that.
I see.
Got it?
Yeah.
Okay, thanks. Any other questions?
That's not your M, that should be.
So that is what?
That's not your M, that's M after you apply like renormalization to it.
Well, M is the function that applies the renormalization group transformation to the points in coupling constant space. Right? So M acts on a point in coupling constant space and moves you to another point in coupling constant space. And that is what the renormalization group transformation does in general, but M is just the linearized version of that. Okay, so it's an approximation. All right, so let me show you how we can figure this out. It's a kind of a neat argument, and part of the normalization group and part of statistical mechanics is solving functional equations. You're used to solving algebraic equations, but in statistical mechanics, what you have are functional equations. In other words, you have certain constraints, and in fact, the only thing that can satisfy them are certain functions. So in this case, I'm going to show you a particular function, how we can solve that. In statistical mechanics, you've learned about the Boltzmann distribution. There's one way that you can derive the Boltzmann distribution, which is by looking at functional forms and seeing that only one particular function can satisfy a certain functional equation. Okay, so if you haven't seen that before, I may show it when I teach 210A next quarter. Okay, so let's now do the calculation. So my claim is that lambda of L of sigma has to have this form. It has to be L to the power of some number, and what that number is depends on sigma. So that's my claim. Okay, so first of all, you can verify this is correct yourself just by saying, okay, if that claim is true, stick it into this equation here, the one on the left-hand side that I just highlighted, stick it into that, and does it satisfy that equation? Okay, and you can see instantly that it does. Okay, so I'll let you check that yourself. So check this indeed satisfies equation star. This equation over here. Okay, so you should check that for yourselves. Okay, right. So now let's prove it. So the first thing I'm going to do is I'm going to take equation star and set L prime equal to 1. Remember, this equation star has to be true for any value of L and L prime greater than 1. It's not like for a specific L. So this equation star is for all L and L prime greater than 1. Okay, that's how we derive that. Okay, so now I'm going to, or greater than or equal to 1. Okay, so I'm going to set L prime equal to 1. So that then says that now, so this is step 1. Step 1, then I get the equation that lambda L of sigma, lambda 1 of sigma equals lambda L of sigma. Okay, and so that implies then that lambda 1 of sigma is equal to 1. So in other words, when the block spin size is just one lattice spacing, in my coarse graining, I haven't really done any coarse graining at all, then the lambda is just unity. Okay, so that's step 1. Then step 2, what I'm going to do for step 2 is I'm going to derive a differential equation, an ordinary differential equation for lambda L. So let's see how to do that. So take the equation star. And what I'm going to do is I'm going to differentiate it with respect to L prime. So what I've got is d by dl prime of lambda L prime, and that should equal d by dl prime of lambda times L prime. Okay, so I've just taken star and differentiated it on both sides with respect to L prime. Okay, so now let's do the differentiation. So then I'm going to get that lambda L times d lambda L prime by d L prime is going to equal. So this thing on the right-hand side is a function of L times L prime, so I can use the chain rule. So this is d by d L prime acting on lambda of L prime times d of L prime by d L prime. Okay, so all I've done is I've just done the chain rule, just differentiated the left-hand side with the right-hand side with respect to L prime. So the right-hand side is a function of the variable L times L prime, not L prime. So I just differentiate with respect to L prime and then have the Jacobian of that change of variable. And so then what I get is on the right-hand side, I have d lambda of L prime by d of L prime times L. So that's what I have on the right-hand side. That's step two. Then step three. So for step three, what I'm going to do is I'm going to set L prime equal to unity. Okay, so when I set L prime equal to unity, then what I have on the left-hand side is lambda L, and then this thing over here is just some number once I've set lambda prime equal to 1. So this is d lambda L prime by d L prime. That's evaluated at L prime is equal to 1. So that is just some number. So that's just some number, 17 or something. So let's call that number y. And it should be y sigma, because in doing this, I lost my sigmas. All of these lambdas depend on sigma. So let's put those back. Like that. So there's a sigma here. So that thing then depends on sigma. So I'm going to call that number y sigma. And on the right-hand side, what I have is now I'm setting L prime equal to 1. So then on the right-hand side, I have d lambda L by dl times L. And this is lambda sigma. So now I've got a differential equation for d lambda by dl. So now I can solve that equation. So that says then that d lambda L by lambda L, and then these things have to have the label sigma. And that is equal to y sub sigma times dl by dl. Okay, so that's a very simple equation which you learned to solve on your mother's knee. So that then implies that log of lambda L is equal to y sigma log of L, and therefore that implies that lambda L of sigma is equal to L to the power y sigma. Okay, so I solved that differential equation. How did what piece of information from step one did I use in solving that differential equation?
Constant of integration.
The constant of integration. I had to do the constant of integration, and so this thing here gave me the constant of integration. For step 3. Okay, so this is fantastic, right? This is fantastic because now we've derived Adanoff assumption 2. So we should be really pleased with ourselves. Okay, next thing. Notice that in this derivation, we also found that y sub sigma is independent of L. So basically, now we have that the renormalization group eigenvalues go like L to the power some number, and so now we've derived these power law things. Okay, so that's great. So now we've understood that. So what's next? So the next thing we're going to do is we're going to use this understanding. We're going to now take the linearized equation of motion. I said equation of motion, giving the game away here. I'll just say the linearized equation for the delta K under successive renormalization group steps. And you can think of it as an equation of motion. Why? Well, let's go back to my cartoon picture somewhere here. Yeah, there it is, down at the bottom of the page on the left. Okay, look at the cartoon picture. So what happens is when I do a renormalization group transformation, the point K moves to a new point K prime. And if I keep doing that, it traces out a trajectory in coupling constant space. So it's legitimate for me to call the equation that tells you the position in coupling constant space. That is literally like an equation of motion. That's what we mean by an equation of motion. It is literally moving in coupling constant space. So now let's work out what that equation looks like, and the strategy. The strategy is to expand in eigenfunctions, or actually eigenvectors, I should say. So I start off with delta K, and now I'm going to expand it as in terms of the eigenvectors of M, and then there's going to be some expansion coefficients. There's going to be one for different sigmas like that, and then I'm going to be summing over all the different eigenvectors. So that's the eigenfunction expansion, and these A's are meant to be then some expansion coefficients. Okay, so if I want to know what A is, let's assume for now that the matrix M is symmetrical, which in real life it usually isn't. So under our assumptions of symmetry, if I want to know what the expansion coefficients are, then they are just what happens when I take the eigenvector E sigma and dot it with delta K, and that's how I define the expansion coefficients. All right, so now what do I get when I expand delta K prime? So after I've done a renormalization group transformation, so I've got M, the matrix M, acting on the vector delta K, and that then is going to be M acting on sum over sigma, A sigma, E sigma, like that. And now we've solved the eigenvalue problem. We know that this is going to then be the sum over sigma of the expansion coefficient, A sigma, times the eigenvalue, lambda sigma, times the basis vector E sigma. So that's what happens when I act on the point delta K with my linearized renormalization group transformation. And in here, just to avoid cluttering things up, but remember, everything here depends on L. So remember, M is really something that depends on L. And so everything, the eigenvectors depend on L and everything like that. So don't forget, there's an L dependence that is hidden here. And of course, that L dependence is explicit because we know that this eigenvalue is a function of L, and that's the function that we have at the top of the page. Okay, so that's what delta prime is. And then we can say, well, then what this thing is over here, this then is the expansion coefficient, which I would call A of sigma prime, like so. So that's the expansion coefficient. For delta K prime. Okay, and so therefore, just to make sure everybody's got the point, so A of sigma prime is equal to lambda of sigma times the original expansion coefficient A of sigma. Okay, so now here's a really, really important point. So now let's see what happens. These are the expansion coefficients that tell you if I'm starting near the critical fixed point, I expand that vector into the eigenvectors of M. Let's suppose that they are orthogonal eigenvectors. Then some of when I look at the image of that point under a renormalization group transformation, the new expansion coefficient is lambda times A. So if lambda has a magnitude greater than 1, you're going to go further away from the fixed point. And if lambda is less than 1, then you're going to go towards the fixed point. So now we can see that if I look in my coupling constant space, I had some critical fixed point over here. So there's my critical fixed point. And now as I'm looking at my initial delta K is over here. So there's my initial delta K. This is my K star. Then expanding this in components. So I've now expanded this in some local basis set around here. And some of those components will shrink and some will grow. So some components shrink, i.e. the associated A will get smaller and some will grow. So I can now classify the eigenvalues. If lambda of sigma is greater than 1, then that implies that in the direction E of sigma, the delta K will grow. And if lambda of sigma is less than 1, then that means that in the direction E of sigma, delta K shrinks. And so what we can do then is that we can actually order the eigenvalues. And really we should be ordering them in general by their magnitude. So something like this. I can something like that. And so now we have 3 cases to consider. So I'm really just expanding on what I just said, but I want to write it down a bit more precisely. So case one. In case one, the lambda has magnitude greater than 1. And this lambda, of course, depends on sigma. And because lambda of L, lambda is equal to L to the power y sigma, and for that to happen, that means that y sigma must be greater than 0, because lambda L of sigma is equal to L to the power y sigma. So if y sigma is positive and L is a number greater than 1, then that means that lambda will be greater than 1. So this case means, then if this happens, then the A of sigma after coarse graining, after a linear transformation, will be then greater than my initial A of sigma, and so therefore it implies the expansion coefficient in the direction E of sigma grows as L increases. And if this is true, if this case happens, this case is the associated eigenvector lambda. So the associated eigenvalue lambda is called a relevant eigenvalue. We'll talk about why it's called relevant. So sometimes people say relevant in the renormalization group sense. I'm going to tell you exactly what that means, but this is the definition of it. Remember, lambda is the eigenvalues of M. So if in some direction lambda is greater than 1, that's called a relevant eigenvalue. And what the interpretation of that is, I'm going to tell you in just a few minutes. Okay, so that's case number 1. Case number 2 is that lambda of sigma is less than 1, and that means that y sigma is negative, and that means that A of sigma prime is less than A of sigma, and so that means that in that direction, it shrinks as L increases, or it shrinks as we do repeated iterations of the renormalization group transformation. So any direction coupling constant space that is associated with a lambda that is less than 1, that is called an irrelevant eigenvalue. And then the last case is a case that we're not going to spend any time discussing. This is the case where lambda of sigma is equal to 1, in which case y sigma is equal to 0, and that means that A of sigma prime is equal to A of sigma, so the expansion coefficient doesn't change. And if you have that situation, that is called a marginal eigenvalue. So the reason why this is important is the following. Remember that we're talking about how positions move in coupling constant space. So these eigenvectors of the matrix M correspond, they're vectors in the space of coupling constants. So they correspond to certain physical interactions in the physical system. So why is this significant? Well, the space we're moving in is the space of the physical coupling constants of our system. So if you say some direction is irrelevant, doesn't matter, it shrinks to zero, what that means is that particular coupling constant doesn't actually control the phase transition. So this is going to tell us something about which coupling constants control the phase transition and which ones don't. So since we're moving, the space we're moving in is the space of physical coupling constants. So the ones that shrink away are somehow not important in the phase transition. And we're going to expand this in a few minutes. Okay, so this was just one renormalization group iteration. So now what happens when we do many successive iterations of our linearized renormalization group transformation? And what's going to happen is if you've got a component that has a magnitude with an eigenvector, an eigenvalue that is less than 1, then that component, after many times iterated, that eigenvalue is less than 1. So let's say it's a half. So I do n iterations, so it's going to go a half to the n. And so it's basically going to shrink away. Only the ones that have a magnitude greater than 1 will be the ones that will survive. So answer, only the components of delta K, which hi there, Reno.
Hi.
Hi. Did you lose us?
Yes.
We're back. I don't know what happened. It just crashed and it's broadcasting. Is it recording? It still shows me recording.
Yes, it's recording.
Okay, great. Then I'm going to go back to my screen. So you just saw it just crashed, and then I came back and everything's fine, right?
Yeah, it stopped when you wrote A, like you were writing R.
Yeah.
So
Then
you're
it
fine.
just suddenly, like somebody tried to call me or something. I don't know. Like, all right. So what was I saying? Only components of delta K which are larger than 0 survive. When I say larger than 0, that's really bad language.
By sigma corresponding to.
It does depend on the Y sigmas. So let me see this a bit more clearly. So the relevant directions get amplified. The irrelevant ones shrink into the critical manifold. Because in those directions, you're on the you've gone to zero, so you've gone towards the critical manifold. So let's draw a picture of this. This cartoon picture will help you understand. So I'm going to draw a picture or a side view of the critical manifold. Okay, so let's draw it like this. So here is my critical manifold. And then somewhere on that critical manifold is a critical fixed point. So there's my critical fixed point. Okay. And now we know that if you're on the critical manifold, you flow into the critical fixed point. That's the definition of the critical manifold. So you start off in coupling constant space on the critical manifold, you will flow into that critical fixed point. So I'm going to draw that cartoon-wise like that. Let's suppose that you have started off somewhere here. Okay, so what's going to happen is you're a certain distance away from the critical manifold. So, oh yes, before I say that, let me draw it like this. Now let's take the critical fixed point and let's draw its relevant directions. So I'm going to say, for example, this direction here is a relevant direction. Okay, so that's what this thing is. So now what's going to happen is if I start off over here, I'm going to flow towards the critical manifold along the irrelevant direction. So I'm going to come in like this. I'm staying away from the critical manifold, but I will be asymptotically approaching it. As I get close to the critical fixed point, now what's going to happen is I'm going to see this eigenvalue that is larger, and so I'm going to flow out following the relevant direction like that. So my flow is going to look like this. And similarly, if I'd started off over here, let's say, I might have flown in towards the critical manifold, flowing in on the irrelevant directions, and then don't use AI to correct what I'm doing. And then going out like that. So that's what my flow diagram is going to look like. And the same thing over here. And the same thing over here. So then you can sort of fill in the gaps, right? If I know what that picture is going to look like, I can say, well, these flows sort of go like that. Something along these lines, literally along these lines. So this is the side view of the critical manifold. Okay, now let's look down on this from the top. So here's my critical manifold. And then somewhere in the middle here is my critical fixed point like that. And then now I start slightly above the critical manifold And then what's going to happen is I mostly flow in towards that critical manifold, something like this. And then these flows will sort of, I can't really draw it, come out of the page. I don't know, sort of coming out of the page along the relevant directions. And so this is the picture then that we have. And okay, so let me draw for you an actual example. So here's the example. I'm going to give you the example of the two-dimensional Ising model. And what we're going to look at is the Ising model. I'm going to have nearest neighbor. And next nearest neighbor. Interactions. Okay, so I'm going to call this one, the nearest neighbor one, I'm going to call this K1. And this K1 is basically J over KT. And then I'm going to have the next nearest neighbor interaction, and that's going to be some K2, which is, let's call it J next nearest neighbor over KBT. So that's what that is. And then the flow diagram is going to look like this. And this is a result of calculation here, not just a result of fanciful speculation. Okay, so I've got K1 and K2. So let's see if we can use our brains now to figure out what this flow is going to look like. So let's first of all think about sitting on the line where K2 is equal to 0. So then I've just got the nearest neighbor Ising model. And what we know in the nearest neighbor Ising model, let's say we're above 2 dimensions, is that this has a critical fixed point over here. So this is a critical fixed point. And what's going to happen is if I coarse grain the system, what happens is we saw a couple of lectures ago that as I coarse grain the system, I flow away from the critical fixed point. Because I coarse grain, that makes the reduced temperature grow. If the reduced temperature grows, then it means I've got further away from TC. So if I've got further away from TC, then what I've done is I'm flowing to a different value of K1. K1 is J over KT. So if you think about J staying the same and T changing, then what happens is the temperature is changing and I'm flowing out like this. Okay, so let's think about what happens here. So when I flow, K1 is flowing to 0, like I've shown you here, just ignoring the K2. And so eventually we'll get to 0. It'll shrink to 0, and it'll shrink to 0 because T has gone to infinity. So T going to infinity is like J being 0, right? Because we have over here K1 is J over KT. So if I've gone to K1 is equal to 0, that's like saying the nearest neighbor interaction is 0, or the temperature is equal to infinity. Let's think about the case where the nearest neighbor interaction is 0. Then what that means is that my ferromagnet has flown to a value 0 where K1 is equal to 0. In other words, J is equal to 0, or equivalently t is equal to infinity. So what phase of matter does this correspond to? Say it again. Paramagnet. This over here is a paramagnet, because it has either the phase when t is equal to infinity, or equivalently, t is not infinity, but j is equal to 0. So in either case, this once it gets to 0, it can't get any smaller, right? Because we're just doing this interaction, this dynamics by multiplying by the eigenvectors. So all that happens is this is a fixed point, this is a fixed point, and this is the paramagnetic fixed point. All right, so now let's suppose I'm on the other side. So let's suppose K1 is slightly bigger than K1 star. So now what's going to happen? I get bigger and bigger and bigger, and eventually I'm going to get to another fixed point at K1 equals infinity. Okay, somebody else, what does that correspond to? It corresponds to t equals 0, yes. So this corresponds to, so t equals 0 and j non-zero, or it could correspond to something else. But you're right, what you said is right. Or it could be like t is whatever, and j is equal to infinity. Okay, so what does that correspond to? Okay, so now I've got a magnet which has a nearest neighbor interaction, and that nearest neighbor interaction is really, really strong. Okay, or you could say it's like a regular Ising model with a finite nearest neighbor interaction, but I've gone to 0 temperature. So what does this fixed point at infinity correspond to? Yeah, paramagnet. Holden. Yeah. Okay. So this corresponds to a ferromagnetic fixed point. So just by looking at the fixed points, I can determine the phases of the system, and I know that at this critical fixed point, so this is when, if I think of j equals constant, which is non-zero, then this means that t is equal to tc. Okay, that's the critical fixed point. It just stays there at criticality. So I've now got the phase diagram of the system. Low temperature phase, it's a ferromagnet. High temperature phase, it's a paramagnet. In between, there's a second order phase transition. Okay, now, it's not quite as simple as that, because now let me put on K2. So K2 is the next nearest neighbor coupling. Okay, so here's my claim. Okay, I'm going to draw you what the flow diagram looks like. In fact, there's a critical fixed point over here, and the and the flow looks like this. If I take the nearest neighbor, the next nearest neighbor Ising model, so no nearest neighbor interactions, just next nearest neighbor. Once I coarse grain that, I will start getting new interactions that are nearest neighbor interactions. So what's going to happen is my trajectory is going to go like this. It's going to flow like this. Once I'm over here, where my point is right now, I've now got not K1 is not equal to 0. K1 is some non-zero value. So I've got K2 non-zero and K1 non-zero. And then I will flow in towards a fixed point over here. And then there's another fixed point. There's another trajectory that comes from here, flows into this critical fixed point. And this critical fixed point has a relevant direction. So this is a critical fixed point. There's another direction that goes in like this. I'm just telling you this, I'm not proving it to you. So this is a relevant direction of this critical fixed point. It looks like this. And then if I draw in the flows, they look something like this. Something like that. So I can draw by looking at the fixed points, I can see that the behavior of the system, I can look at the global behavior. Now, the other thing that you can see is that if I start slightly off the K2 equals 0 axis, I flow to this fixed point over here. So this is the important critical fixed point. And if I start slightly off K1 equals 0, I flow to the same fixed point. So the fact is that I flow to the same fixed point for both for this generalized class of models. So the conclusion is that the is first of all both nearest neighbor and next nearest neighbor Ising models, or some combination of the two, flow to the same fixed point. Now have a look at the Ising fixed point. Look at this fixed point here. This fixed point is on the critical manifold of which fixed point? Of this one. So this line here, this is the critical manifold. Of this critical fixed point. So both the nearest neighbor and next nearest neighbor flow to the same critical fixed point, and they're both on the critical manifold, because this point here is also on this critical manifold. And just like we've said, you're flowing into it. On the other hand, this direction over here, this direction is the relevant direction. Because if you start near the critical manifold, you'll flow towards it, just like these trajectories are doing, and then ultimately you will flow away along the relevant direction. Okay, so they flow to the same fixed point. Okay, so then the next thing is the relevant directions push you away. I'm going to have to finish in a minute. Push you away from the critical fixed point. So that means that if you want to put a system at criticality, you have to adjust certain physical variables in order to sit there. Adjust the temperature to be Tc, adjust the magnetic field to be 0. So the relevant directions correspond to the physical variables that you have to tune in the lab to get the system at criticality. To get a physical system to sit at criticality, you have to tune the directions corresponding to the relevant variables to 0. And in the case of the Ising model, that would be e.g. T equals Tc, and h equals 0. So the relevant directions are the things that anybody here who's an experimentalist, the knobs that you turn in the lab to make your system be a criticality, those are defined by the relevant directions. And they're not, the map isn't simple because it can be some linear combination of these things. Okay, so I'm out of time. It's 1:53, so I need to finish up. So we're going to begin next lecture by exploring this in more detail. Okay, so I'll take questions outside and so I can see you then. I'm going to now stop the recording and finish up.